All right, let's get going today. Um, for those of you wondering, the exam results should be available for you to view now. So if you have any questions about that, let me know. Uh, yes, yeah. So we can do that during after class or in office hours. Okay. So anyone can go and view their own results, and then if you want to talk about them with me, I'm happy to do that. The other thing I'll warn you about as we get started today is I seem to have misplaced some of my notes, so I'm going to be winging it today. So if it's a little rough, so let me know how I do at the end. But um, I will make sure that doesn't happen again. All right, so we're going to continue on with stuff we talked about last time. So we finished last time talking about calorimetry, and we focused on relatively simple examples of calorimetry where we're doing the reaction in an aqueous solution inside of a calorimeter. The water that's part of that solution would be what would be absorbing the heat from the reaction. And we're talking about, again, aqueous chemical reactions, precipitation, acid-base, stuff like that. We're going to start today with a little bit just of an extension of that. It doesn't really change things too much from your standpoint in terms of how you approach the problems, but a slightly more intricate and accurate type of calorimetry, which from an experimental standpoint, that would be important for our purposes. As I said, it doesn't change the story too much. So this is called constant volume calorimetry, and there's a little diagram of it over here. And essentially, there's a couple of advantages of constant volume calorimetry. One, because it's totally sealed, you get less or essentially no, not exactly no, but pretty much no heat loss to the surroundings. If you're doing an experiment in sort of a simple coffee cup calorimeter, there is the possibility of some heat escaping, especially if gases evolve during the reaction, and they have to be vented to keep them at constant pressure. But in a constant volume calorimeter, it's a totally enclosed system. So there's less and essentially no heat loss to surroundings. So that makes it more accurate in terms of the temperature readings. The other big advantage of this, this actually a question like this came up in an email from a student of like, well, how do you do a combustion reaction in a calorimeter because there's water everywhere? Good point. But you can do it in a constant volume calorimeter because you have this little compartment in here is a little sealed metal container where the actual chemical reaction takes place, and then that's going to be surrounded by a bath of water that will absorb the heat from that reaction. So in a constant volume calorimeter, you can do combustion reactions or any reaction that involves gas phase reactants or products. Combustion reactions are a very common application of calorimetry for a few reasons. We'll get into this a little bit at the very end of this chapter. But essentially, combustion reactions are common in calorimeters because if you want to analyze, for example, the energy content of a type of fuel, how much energy does this fuel contain per gram, per mole, whatever you want to do, you can do that in a calorimeter by burning some small amount of it and measuring the heat from that. The other big application of calorimetry is in food science. So when you read the back of a food label to see how many calories it has, we haven't talked about this unit, but calories is just another unit of energy. It's about 1/4 of a joule, 4.184 joules per calorie. And so when you read how many calories something has, they determine that by essentially burning the food in a calorimeter and figuring out how much energy is released when that food burns, which is sort of analogous to what happens inside of your body, although of course not in a combustion reaction. All right, but anyway, in a constant volume calorimeter, we can perform combustion reactions or other reactions that involve gases, so we're not limited to just aqueous reactions or simple heat transfer processes. Now, the equations for this are basically the same. So we already introduced last time how to calculate the heat for a calorimeter, where there's going to be two terms involved. Now, all the examples we did last time were based on the assumption that all of the heat is absorbed by the water. So we only used this term last time, MC delta T, where M is the mass of water in the calorimeter. We also have the second term here, which we have not yet used in an example problem, but we will today. And in constant volume calorimetry, it is much more common to include this. The constant volume calorimeters, as you can see, are more complicated. So experimentally, what you would usually do is you would separately measure the heat capacity of the calorimeter by itself and then add into that whatever water is in there. And so it's more common to see both of these terms in that context. But again, it's no different than what we introduced last time. So that's really the only equation. And then following it from the same standpoint, we're typically, especially in a constant volume calorimeter, you're measuring some sort of chemical reaction and what the enthalpy change is for that reaction. Heat of reaction is equal to the negative of that. Now, the one thing to be a little bit familiar with is in a constant volume calorimeter, because it's at constant volume, the heat of reaction at constant volume is related to delta E. But keep in mind that delta H and delta E in this context are going to be used interchangeably. So don't get too hung up on that. You should probably be aware just from a definitional standpoint that in a constant volume calorimeter, because you're not allowing the pressure to remain constant, the heat of the reaction that you measure, and then if you normalize it per moles, it's technically a delta E. But as we talked about last time, delta E and delta H are usually very similar to each other. So if we ask you to measure the enthalpy change in a constant volume calorimeter, don't get all hung up on those definitions. Just do it the way you normally would. So it is technically delta E, although we're typically going to still refer to it as delta H, and they're not that different from each other. But if you're just trying to be really precise, you should be aware of that. All right, so let's do an example of this. So here, a 3.45 gram sample of octane, so octane is one of the major components of gasoline, is burned in a constant volume calorimeter that has a heat capacity of 9.121 kilojoules per Kelvin, or you can remember we can replace that with degrees Celsius. Those are interchangeable in this context. If the temperature of the calorimeter rises to 17.7 degrees Celsius, what is the combustion enthalpy of octane in kilojoules per mole? So we're going to start in a calorimetry problem, almost every case, especially if it's talking about a chemical reaction in a calorimeter, by calculating that heat term that we just talked about. Now, I'm very careful when I write this out to always include in this equation mass of water. That's the mass that matters when we're calculating the heat that would be absorbed by the calorimeter during a chemical reaction, or the heat given off by the calorimeter if it's endothermic. So in this case, we look through the information in the problem. We're given a mass. So a lot of people make the mistake of, okay, I'm going to put that in here for mass. But remember, the mass that we would need is the mass of the water in the calorimeter. This is the mass of the substance that's involved in the reaction, which we don't need right now. So in this problem here, we did not actually give you anything about the mass of the water, how much water is in the calorimeter. We're just telling you an overall heat capacity. So unlike last time, we're actually going to not consider this term. So as I said, there's three possibilities for how this is going to be set up. And sometimes you'll need both of these terms if you knew the mass of the water in the calorimeter and the heat capacity. Here, we're just giving you the overall heat capacity. That number includes the calorimeter itself, any water in the calorimeter. We just kind of all grouped it together into one term here. And you also know that the units for this are kilojoules per Kelvin. So there's no mass term involved in this. It's just multiplying that number by the change in temperature. So that's how we're going to get the heat for the calorimeter in this case. You have to pay attention to units when you do this. And so what we get in this case is we just have that term there, which is 9.121 kilojoules either per Kelvin or per degree Celsius. And we're going to multiply that by delta T. Temperature rises 17.7 degrees Celsius. So it's going to be a positive 17.7. And so when we multiply those out, I have to do this on my phone because I forgot my notes. And I'm terrible at using a phone because I'm old. Here we go. So we get 161. That should be enough sig figs. 161 kilojoules. That's already in kilojoules because that was the unit of the heat capacity that we had here. So that's the heat for the calorimeter. Now what we're looking for, though, is the combustion enthalpy in kilojoules per mole. So what we have to do then is make the simple relationship that the heat of the reaction, which would be the heat involved with combusting 3.45 grams of octane, is just equal to the negative of that. So trivial next step is to say that the delta H, the heat for this reaction on this scale is minus 161. But then the last thing that we want to do is say delta H of combustion is going to be the heat for our reaction divided by the moles of substance, which is octane, C8H18. So we typically report enthalpies of any type, really, per mole of substance, that they can be normalized to that amount. And so we're gonna have to do this last step here, because this, as we said, this minus 161 kilojoules is the enthalpy change when we burn 3.45 grams of octane, but what we want to report is the enthalpy change when we burn 1 mole of octane, so we have to divide those two quantities. So that number we have to do a conversion to get moles. So I'll do it up here since I'm a little bit out of room. We need the moles of that substance that we're burning. So this is where the mass of substance comes into play. As I said, it doesn't come into play when we're calculating the heat for the calorimeter. It just comes into play at the end when we need the mole of substances. So we have 3.45 grams of C8H18. 1 mole of that, we're giving you the mass, is 114.23. And so again, no, I have some on my notes, but not this page. So let me work it out real quick. And so we get 0.0302 moles. So that's how many moles of substance we burned, which led to 161 kilojoules of heat being released. So if we divide the two numbers, that'll give us how much heat is released if 1 mole of substance is burned. That gives us kilojoules per mole, which is what we're looking for. We divide those two, and we should get something like negative 5.33 times 10 to the third kilojoules per mole is the combustion enthalpy. Combustion enthalpies are always negative because, as we said, if you have an exothermic reaction, that means heat is being released. When we burn something, we're releasing heat, of course. So I hope I didn't mess up any of the math doing it on my phone. If anybody followed along and got something different, let me know. Seems like we're all reasonably pleased with that effort. Okay, so then any questions on that? Yeah. So then so that's how we would go about it. It's really, it's a different type of calorimeter experimentally, but it's no different in terms of how we approach the problem. It's still just calculating the heat for the calorimeter using one or both of these terms. That relates to the heat of reaction just by putting a minus sign on it, and then normalizing to moles of substances gives us the value that we would report. Okay. All right, so that takes care of the calorimetry section, which is a fairly significant portion of this chapter. But what we're going to move on to now is how we can actually calculate delta H for a reaction, not using experimental data, but actually using sort of tabulated data for other chemical reactions. So if we have some chemical reaction we want to find delta H for, and we know delta H for a bunch of other reactions, we can learn how to piece those together to get the unknown delta H that we're looking for. So to understand how this works, first we have to talk a little bit about what are called consecutive reactions, because what we're going to be sometimes doing in this part of the course is we're going to be taking two chemical reactions, and sort of combining them in some way, usually adding the two together to get a new chemical reaction and then relate the delta H's. So that's what we're working towards. So the nice thing is this isn't too difficult to deal with, because we can add together chemical equations just like we add together mathematical equations. So if you learned, I don't know what course you would have learned this in, probably in high school, most likely, or if you took college algebra, you probably saw it there, where if we have systems of equations, systems of two or more equations that we want to solve, we can add those two equations together, where you add everything on the left side of the equal sign together, everything on the right side of the equal sign together, and then you can sometimes simplify from there. We can do the exact same thing with chemical equations. So I'm going to try to make one up here that it works out. So let's say, we'll just do it generically. Let's say we have a chemical equation, 3A plus 2B forms C plus D. Let's just do that. And then let's say we have a second chemical equation that would be something like that. All right, again, totally generic, but we have two reactants, two products in the first equation, one reactant, two products in the second equation. And then, as I said, we can add these together just like we would a mathematical equation, where everything on the left side of the arrow gets combined as reactants in the combined equation, everything on the right side of the arrow gets combined as products on the right side of the arrow. So we have 3a plus a is 4a. We have 2b on the left side. So those are what we have on the left side of the arrow. And then on the product side, we have another 2b from there. Whatever order you do it in is fine. We have c plus 3c, so we have 4 c's, and we have a d from there. So that's what we end up getting. Now, what you'll notice in this equation and what sometimes happens, and what we're going to intentionally have to do for some of the applications of this concept, is that we will have the same species on both sides of the arrow. And so mathematically, if you have the same thing on both sides of the equal sign, it subtracts out and goes away. Same exact thing for a chemical equation. We have 2b there, 2b there. So what we would call in this case, or we'll just call it, sorry. So if we have that situation, something that's on both sides of the arrow, we call it, it can be called an intermediate. And so what's meant by that is it forms in one of the equations and then is reacted in the other equation. So it's an intermediate species that forms then goes away. I wrote them in the opposite order here, but that's what essentially happens. It's on both sides of the arrow, and so it can cancel out. So we're going to cancel out the two b's, and our simplified equation will just be 4a going to 4c plus d. Okay, so whatever's on both sides of the arrow will cancel out just like it would in a mathematical equation, it just subtracts out. Because again, there's no net change for B. We have two B's as a reactant, forming two B's as a product, so nothing's happening to that, so it doesn't need to be there in the equation. So that's how we can combine chemical equations. We just add them together, and anything that's the same on both sides of the arrow subtracts out. Now, when we do this, though, in the context of delta H that we're working towards, a lot of times the two equations that we're given, they're not going to have the same coefficient for that intermediate. So usually what we're doing, we're combining two equations, is we want some or all, some of the intermediates to cancel out to simplify the equation, but sometimes they don't have the same coefficient. So if they didn't have the same coefficient here, we would have had to adjust one of them. So when we're combining two or more equations, the set of steps that would be involved is going to be, I mean, first you have to, usually they're given to you in this context, but you have to write out the two or more than two balanced equations. And then you have to identify intermediates because the way we typically do this, we'll see examples. It'll make more sense when I do examples, is we want to find a chemical equation of some sort that we're going to find delta H for, and we're going to generate that chemical equation by adding together two or more other equations where we know delta H for those equations. So what usually happens is the equations that you're given that you're going to be combined together, they're going to have one or more intermediates in them that you don't want to be present in the final equation. You have to figure out how to get rid of them. So you have to identify what those are. And then sometimes what you have to do, in most cases you have to do, is you have to multiply the coefficients in one or more of the equations to ensure that the intermediates cancel out. All right, so if we have intermediates that are in the given equations, but we don't want them to be there in the final equation, we have to make sure that their coefficients are the same on both sides of the arrow. And if they're not already the same, we might have to take one or more of those equations and multiply them by some common factor to make that that true, to make sure that the coefficients of the intermediates are the same. Again, this will all make more sense when we do examples, but that's sort of the next thing to do. And then once we've done that, then we just combine the equations and cancel out the intermediates, subtract out the intermediates. All right, so that's the last step. Yeah, go ahead. Yeah, we'll see how that works. So when you multiply coefficients in one or more of the equations, to ensure that those equations stay balanced, you have to take every coefficient in that equation and multiply it by that same factor. Um, now, what that's going to lead to is an intermediate equation where it's not written in terms of the lowest whole numbers often, but then once you combine the equations, that'll take care of itself because you're doing that just to make sure that the intermediates cancel out. But because the equations you're starting with in step one are already balanced, if we have to multiply any of those by a factor to take care of the intermediates, that we have to take the whole equation, every coefficient in that equation, and multiply it by that same factor to make sure that it remains balanced. So we'll see how that works, but that's a good question. It's something you have to be aware of when you do this. You can't just change one coefficient randomly. You have to change all the coefficients in that equation by the same factor if you're going to adjust them in any way to make this work. All right, any other questions on just the generic framework? All right, so let's see how it works then. So we have this reagent here, POCl3, and it can be prepared in two steps. In the first step, you take elemental phosphorus. We'll learn later on today or next lecture that phosphorus has the standard form P4. It's a tetraatomic element. And then chlorine, which is Cl2. So you can combine those to make PCl5. And then in the second step, you take PCl5 and react it with water to produce POCl3 and HCl. So we're doing a two-step here. We're going to combine them into a single chemical equation. So when we do this, here we have to actually write out the two equations that we're going to combine. In most cases, for this part of the course where we're using this to find a delta H, like we're going to learn in a little bit, we would give you the equations. You wouldn't have to come up with them yourself. But here we're going to do that. So we have to read the text that's given to us and come up with the individual equations. So
I'm thinking other is better than you.
So I think there's somebody in Teams that's not muted. Could you please mute yourself? Thank you. All right, so if and I'm sorry, it's hard for me to answer the Teams questions when I'm in full screen like this. So if we have a question, you can try to shout it out, but it's probably hard for me to deal with that. So all right, so we have the first step is going to be P4 combining with Cl2 to make PCl5. So we have to balance this equation with the correct coefficients. This one is technically a redox equation. We probably don't have to go through all those steps to balance it because there's just a few things involved. So we have 4 phosphoruses on the reactant side, so that needs a coefficient of 4. If we do that, we're going to end up with 20 chlorines, so we need a coefficient of 10 there. All right, so I think that should be balanced. Pretty simple. And then in the next step, we take PCl5. I think this equation we actually saw once earlier if you have like a really close to photographic memory. PCl5 combining with water to make POCl3 and HCl. This is technically an acid-base equation, although it doesn't look like one, but we can balance it again by inspection. So 2 hydrogens from water, so we would need 2 HCl's, and I think that's the only coefficient we then need. PCl5, 1 phosphorus, 5 chlorines, 3 plus 2 is 5, 2 hydrogens, 1 oxygen, so just a single coefficient needed. So then if we want to combine these into a single equation, though, what we notice is that in this first equation, we're forming PCl5. That's then reacting in the second equation. So that's going to be our only intermediate here. Again, an intermediate is something that would form in one equation and go away in the second equation, or vice versa. So basically, it's on both sides of the arrow, PCl5. But what we notice here is that in the first equation, PCl5 has a coefficient of 4, but in the second equation, it only has a coefficient of 1. So if we were just to add these two equations together right now, the PCl5 or intermediate would not completely cancel out because there'd be 4 on one side, 1 on the other. They don't subtract out properly. So that's where we take that second step there. We identify that PCl5 is the intermediate. And we're going to multiply this whole thing by 4 to make sure that the PCl5 has a coefficient of 4 on both sides. But as we said, and as the question came up earlier, when we do this, we need to multiply every coefficient in the second equation by 4 to make sure that it stays balanced. We did a little bit of effort to balance it. We don't want to undo all that effort by just randomly changing coefficients. So every coefficient gets multiplied by 4. So the modified equation is going to be 4 PCl5 plus 4 H2O goes to 4 POCl3 plus 8 HCl. So we modified the second equation by multiplying everything by 4. And then what we're going to do is we're going to combine these two equations here. The original first equation, which has 4PCl5 forming, and the modified second equation in which 4PCl5 will be on the left side of the arrow. So when we add those together, what we're going to get is P4 plus 10Cl2 from the first equation, 4PCl5, and 4 H2Os from the second equation. And then on the right side of the arrow, we have 4 PCl5 from the first equation, and then 4 POCl3s, and 8 HCl's from the modified second equation. So again, it's this one here that we're adding to this one down here, okay? So what we see then is that we now have, of course, 4 PCl5 on both sides of the arrow, so it cancels out. And then our final equation would, when we cancel it out, would be P4 plus 10Cl2 plus 4 H2O goes to 4 POCl3 plus 8 HCl. Okay, so there's a lot of coefficients there, but it remains balanced if we did all those steps correctly. And it is smallest whole number coefficients. We can't get any smaller than that without having a fractional coefficient in P4. All right, so any questions on that? So that's how you do it. As I said, though, the real purpose of all of this that we're getting towards is using this to find delta H. So as a preview of what's to come, what we'll often see is that we're going to give you delta H for the first and second equations here. And then you have to use that information to find delta H for this final equation there. So that's what the real purpose of this in this part of the course is. Yeah, go ahead. You'd have to find the factor you'd multiply by such that both intermediates cancel out. It's not common, I would say, if we're only giving you two equations, I wouldn't say it's common to have more than one intermediate. It's not impossible, but we will always give you equations that work out. I know we have a reputation of being cruel and evil, which I resent, but we would not give you a series of equations where you cannot cancel out the intermediates that need to be canceled out. It's not something that we would do to you. So there is a way to do it, and like I said, usually with two equations, there'd just be one intermediate to worry about. But in systems of 3 or more equations, there might be more than that, and you have to kind of take all of them into account. But I'll show you kind of how to approach that a little bit more logically, so that it doesn't become too big of a puzzle for you. All right. So that's the portion of the lecture today that I had to wing, so I didn't have notes for it. So hopefully it went okay. Now we're going to proceed on with the normal approach. So as I said, what we're getting towards is using this to find delta H for a chemical equation. So we also then have to understand if we're going to start adjusting coefficients in chemical equations and adding them to each other, what does that do to the delta H's of those equations? So the first is that we already talked about the sign of delta H a lot. It depends on whether the reaction is endothermic or exothermic. So it can be either. So if you have a delta H given to you that's negative or positive, as long as you're not flipping the direction of the reaction, as long as the reactants are still on the left side, products are still on the right side, you're not changing them around, your sign is going to always stay the same as what it is. You're not going to ever change the sign of delta H unless you flip the equation, as we'll talk about later. But what's important now for this is to understand how the magnitude of delta H changes, because we kind of saw this in calorimetry, but the delta H for a reaction is proportional to the amount of substance that's involved in that reaction. So if we have the combustion or the decomposition of water into its elements, I think this number is liquid water going to gas phase H2 and O2. But anyway, so if you have H2O liquid going to hydrogen and oxygen decomposing, the delta H for this is endothermic and is 286 kilojoules. Now, what's important for us to recognize in this is that when we write delta H as 286 kilojoules next to this chemical equation here, that means if we take 1 mole of water and we decompose it to make 1 mole of H2 and half a mole of O2, that's going to be delta H for that equation. So if we're producing 1 mole of hydrogen, as this exactly is written, the delta H would be that number there, because there's a coefficient of 1 in front of hydrogen. But let's say we were breaking down water and instead we wanted to produce 2 moles of hydrogen, same equation, but now we're producing 2 moles. We would have to double the delta H. Because this 286 kilojoules is the enthalpy change for 1 mole of hydrogen, but if we're doing 2 moles, we have to double it. So that's going to come into play, as we'll see, when we adjust coefficients of a chemical equation like we did in the last example. If you multiply them by some factor, the delta H also gets multiplied by that same factor, because the delta H that's given applies to that specific set of coefficients. If we change the coefficients by some factor, we change the delta H by the same factor. Okay? Now, the other thing that we're going to sometimes have to do, we did not see it in the example that I just did, but sometimes when you're combining chemical equations, you have to also take one or more of them and flip the direction of it to ensure that your intermediates cancel out and to ensure that you get the correct reactants and products on the overall equation you're trying to find. So sometimes you have to reverse a chemical reaction. So that's the situation where delta H would change sign. So if we take, for example, I'm just giving some random examples here. We take magnesium carbonate and heat it up to a really high temperature. You're going to produce magnesium oxide and carbon dioxide. You'll blow off CO2 gas. This is an endothermic process. You have to put heat into it to get this to occur. It's positive 117 kilojoules. But let's say we instead were interested in the opposite reaction. So we flipped the reactants and products in this, and we wanted to take MgO and react it with CO2 to make MgCO3. So if we're talking about the reaction in this direction, delta H is the same magnitude because all the coefficients are still 1, but we flipped reactants and products. We flipped the direction of the whole equation, so that means we flip the sign of delta H. Because remember, delta means final minus initial, which in the context of a chemical reaction means products minus reactants. So if you switch the products and the reactants, you would then flip the sign of delta H as well. All right, so that's what happens when we change the sign. And then as we kind of already alluded to, if we change the coefficient, delta H would scale by the same amount. All right, so if we were to take this first equation here and double it, let's say one of these things is an intermediate that we need to double to get rid of it. So we take every coefficient and double it from the first equation here. We would have to also double delta H. So the given delta H for coefficients of 1 across the board is 117. We'd have to double that to get the correct delta H when the coefficients are also doubled. All right, and then sometimes what we'll have to do also is use fractional coefficients to get intermediates to cancel out things. So if we took this second equation, or sorry, this first equation here again, and we halved the coefficients, it's not as common to have to do that, but sometimes you do have to put fractional coefficients on things to get the intermediates to work out. We would have to also multiply delta H by 1/2. Okay. So as we're going through and adding up chemical equations to remove intermediates, as we said, we sometimes have to flip the sign and or adjust the coefficients. Flipping the sign changes the sign of delta H. Flipping the direction of the reaction, I should say. Scaling the coefficient scales delta H by the same amount. So mathematically, it's not too complicated, but you have to remember to do that. So then what that leads us to is what's called Hess's law. So Hess's law states that if we combine two or more chemical equations by adding them together, the delta H values are also additive to one another. So it's again, mathematically not too complicated. If we're combining two or more chemical equations by adding them together, the delta H values for those are also additive. All right. Which means that the delta H, the total delta H for a series of equations that we're adding together, if we're doing two or more, is just going to be the delta H of the first equation that we're adding, plus the second, plus the third, however many there are. Again, it's sort of calibrating yourselves on how cruel and unusual we might ever be. Typically, in the homework assignments and exams, you won't see more than 3 equations you have to combine. There might be rare exceptions to that, but 3 is about as high as we'll go. Okay, so then if we want to take forward then with an example. So if we have this first equation here, that I just gave you, we know the delta H is 117 kilojoules. And then let's say I give you another equation here, which is the hydrogenation of carbon dioxide to make methanol. This would be like the world's most roundabout way to make methanol, but on paper it works. Delta H for this reaction is minus 131. So if we want to combine these two equations, what we find is that CO2 is the intermediate. Carbon dioxide is formed in the first equation. It's a reactant in the second equation, so it appears on both sides of the arrow. So it cancels out. We don't have to adjust the coefficients because it has a coefficient of 1 in both cases. So when we add these two together, the CO2 cancels out. So I won't even write it out as a separate step. I'll just cancel it out now. And then what we have left on the left side of the arrow is MgCO3 plus 3H2. On the right side of the arrow, we have MgO from the first equation plus CH4O and water from the second equation. And so the delta H for this combined equation here, the total delta H is going to be just the sum of delta H for the first and second given ones that we added together. 117 kilojoules plus minus 131. So just pay attention to signs when you're doing this. And that adds up to minus 14 kilojoules. So the delta H for that equation there, again, a very roundabout way to make methanol, as it turns out, but nonetheless, we can add together, get delta H of minus 14 kilojoules for that. So when we add together equations, you just add the delta H's. But as I said, we're going to do a bunch of examples now where very often you have to adjust or flip one or more of the given equations, get them to add up correctly. And so that means you have to take care of the delta H's in those intermediate steps before you add everything together at the end. All right, any questions so far? All right, so like I said, we'll just do a series of examples with 2 or 3 equations. All right, so here's the way that these problems are typically going to be set up. We're going to give you an equation. This one is the dimerization of NO2, 2NO2 making N2O4. And we want to find the delta H for that. And we're going to give you 2 or more other equations where we know the delta H. So we have to figure out how do we combine these 2 equations to get the overall equation, and then we have to add the delta H values as we just did. So when you're looking through this, what I like to focus on is we look at the reactants and products of our given of our overall equation here, 2NO2 going to N2O2, N2O4, and find out which of these 2 equations does it show up in. So the reactant NO2 shows up here in this first given equation, but it's on the product side. So what we want for this equation is we want NO2 to be on the reactant side, and we want it to have a coefficient of 2 in front of it. So what we're going to be doing is we're going to take this first equation here. I like to number them to keep track of them a little bit. So this first equation here, we're going to flip it, which is equivalent to multiplying by minus sign, and we're going to double the coefficients. So I would say when you're doing this, you don't usually, at least initially, you don't want to worry about intermediates right away. We talk about intermediates a lot and trying to make sure they cancel out, but typically the way you would approach a problem like this is look at the reactants in the products in the equation you're trying to find and figure out where they show up in the given equation, especially if they only show up once in the given equation. NO2 is only shown here in this equation. We just figure out how do we modify this equation to make sure that NO2 is where it's supposed to be and has the right coefficient. So we want NO2 on the reactant side. We want it to have a coefficient of 2, so we need to take this first equation, flip it so that NO2 goes to the reactant side, and we have to double the coefficients to make sure it has a coefficient of 2 in front of it. So that's equivalent to taking minus 2 times the first equation. So that's going to take this first equation and flip it and double the coefficient. So it's going to become 2NO2 going to N2 and 2O2. And then the delta H is going to be taking this delta H and multiplying it by -2 because we flip the reaction, so that changes the sign, and we double the coefficients, so that scales it by a factor of 2. So we're going to take -2 times delta H1, which is 34 times -2, which is -68 kilojoules. So that's the modified equation 1 that's going to put 2 NO2s on the reactant side where we need them. And then if we look for N2O4, N2O4 is here in the second equation. It's already on the product side, which is where we want it. So we don't have to flip the second equation. And it already has a coefficient of 1 in front of it, which is what we want for this equation up here. So because N2O4 is already on the correct side of the arrow, and because it has the right coefficient, we don't have to do anything to that second equation. We take it exactly as is. It's just going to be N2 plus 2O2. So we could have focused on the intermediates a little bit, but nonetheless, if we just focus on reactions to products, the intermediates should take care of themselves if we're doing everything correctly. So we get equation 2 unmodified, so that means the delta H is the same. And so now we're ready to add everything together. So when we add these two equations together, on the left side of the arrow, we have 2NO2. We have, from the second equation, N2 plus 2O2, but those are going to cancel out with the N2 plus 2O2 that are on the right side here. So N2 cancels out, O2 cancels out. They're both on each side of the arrow. And then the only product that's left is N2O4. So we've added these correctly to get the equation that we're looking for. And then the delta H is just going to be these two numbers added together. We've already modified the values, so we just add them together now. Minus 68 kilojoules plus 10 kilojoules equals minus 58. All right, so doing these problems is a little bit like a puzzle because you have to figure out how we combine the two equations, or sometimes more than two equations, to get what we're looking for, and then what happens to the delta H values as we do that. Once that's all taken care of, then it's just adding at the end. So that the last step is the simplest if you've done everything correct up until then. All right, any questions on that? All right, we'll go to a slightly more complicated one that involves 3 equations now. So we're trying to determine the enthalpy change for this reaction. The formation of C2H2 is called acetylene. So if you've ever seen an acetylene torch, that's what that is. And just the formation of that from the elements, 2 carbon plus H2 to make C2H2. Now, the equations that we're given don't really look anything like that. So, but as I said, the way that we're going to approach this is we're going to number the equations that we're given. That's just a helpful thing that I like to do for myself to keep track of them. And then we're going to figure out how to rearrange them to get the reactants and products from this equation here in the correct order and with the correct coefficients. So it doesn't really matter what order you approach things in, but if we look at this first equation here that's given to us, we have C2H2 as a reactant, but that's supposed to be on the product side for the reaction we're trying to find delta H for. So what we need to do for this first equation is flip it to make sure that C2H2 ends up on the product side. The coefficient is already correct. It's a coefficient of 1, so no scaling of the coefficients. So we're going to flip the first equation here. That's going to put C2H2 on the product side. So it's going to be 2CO2 plus H2O goes to C2H2 plus 5 halves O2. And then the delta H for this is just going to be the negative of the given delta H. So this delta H is minus 1299.5. We flip the direction of the reaction, so we just have to flip the sign of delta H to make it positive 1299.5. So that's how we modify the first equation. For the second equation, this one has carbon in it, which appears here in the reaction we're trying to find. So we have carbon on the reaction side, so it's on the correct side of the equation, but the coefficient for carbon is 2 in the equation we're looking for, but it only has a coefficient of 1 in the given equation. So we're going to have to double that one, get the coefficients to be correct. So we're going to take this whole equation here and double it. So it's going to become 2 carbon plus 2 O2 makes 2 CO2s. The delta H for that is going to be 2 times the second delta H because we doubled the coefficients. So it's going to become this number here multiplied by 2, which is minus 787. And then finally, what we have to look for is the last substance from this equation that we haven't taken care of is hydrogen. Hydrogen appears in the third equation. It's on the correct side of the arrow. It's a reactant, and it has the right coefficient of 1. So we don't have to do anything to the third equation. We're just going to add it in. So it's just going to be exactly as written. No change to that one. Once we figure out how to modify the equations to get the reactants and products on the right sides of the arrow with the right coefficients, we modify delta H, and then at the end, we just add them all together. Yeah. So the last step, as I said, is easy, but the steps before that are the key to getting it right. So you have to, you can't get too excited about getting that last step. You have to do this first steps. So, but for this one here, we don't have to flip anything or change any coefficients. So it just stays exactly the same with the same delta H. Nothing was modified there. And I think this is one also where, you know, in a problem like this, trying to focus on intermediates becomes problematic in most cases because, for example, one of the intermediates here is O2. It appears in all of our given equations, but not in the final equation. So what combination of coefficients would we want to do to make sure O2 cancels out? That's really hard to figure out. There's really impossible to figure out because there's a lot of combinations that would work. So that's why we're focusing on the reactants and products in the given in the equation we're trying to find, and making sure we modify the given equations according to that. And then if we do everything correctly, the intermediates should then cancel out. So when we add all these together, what we have is we have 2 CO2s on the left side, but that's going to cancel out with those 2 CO2s there. We have H2O from this equation on the left side, but that cancels out. So we have the 2 carbons that we need. That doesn't cancel out with anything. All right, here's one that's a little bit tricky to think about, O2. So we have 2 O2s from this equation on the left side, plus another half from this equation on the left side. So that would be 2.5 or 5 halves O2. But those are going to cancel out with this 5 halves O2 that's on the right side. So if you like to write everything out, you can. I tried to sort of do it in my head and skip that step. But 2 plus a half is 2.5 O2s. But we have 2.5 or 5 halves O2 over here on the right side as well. So that all cancels out also. It should work out if you did this correctly. And then we have the H2 that's left on the left side, doesn't cancel out. And then the only thing left on the right side of the arrow is C2H2. So if you have the time, it is good to check yourself to make sure that the equations add up correctly. If you're in a hurry, I suppose you could trust yourself that you did it correctly and skip that step. But we can verify that we get this equation. And then as the question came up earlier, the delta H now is just going to be these 3 modified delta H values just added together. So 1299.5 kilojoules plus minus 787 plus minus 285.8. So we just add those all together, and that's it. Okay, so again, the hard steps is sometimes figuring out how to rearrange the given equations. Once you get that, you just take whatever delta H's you have and add them all together. All right, any questions on that one? All right, we'll just do, I think, one more to solidify that. So we want to calculate kind of a not too different one, but here we're talking about the formation of carbon dioxide from its elements instead of C2H2. Now, again, this one is like totally ridiculous because we're giving you all kinds of equations that involve strontium oxide, strontium carbonate, and what we're trying to find is a reaction that involves carbon and oxygen only. So it's like kind of a ridiculous way to do it, but it does work on paper, and it's a fun exercise nonetheless. But we're going to follow the exact same approach. So it's looks a little bit more complicated maybe because there's so many elements in here, especially strontium, that don't even appear, but we can follow the same approach. So what we want is we want carbon to appear on the reactant side with a coefficient of 1. As I said, it doesn't really matter what order we do this in. So what we find is that this equation here has carbon on the product side with a coefficient of 2. So for equation 3, if we want to get one carbon as a reactant, we have to flip it, and we have to multiply the coefficients by 1/2 because this has a coefficient of 2. The overall equation has a coefficient of 1. So sometimes you can go either 1, 2, 3 in that order and figure out what to do with them, or if you want to go through just the reactants and products that are given to you, you can do it that way as well. So we have minus 1/2 times equation 3 is going to allow us to get one carbon as a reactant. So we flip it and have the coefficients. So it's going to become strontium. I'm going to leave out the states of matter. Plus 3/2 O2 goes to strontium carbonate. So we took that third equation here and we flipped it, multiply the coefficient by 1/2. That gets carbon here as a reactant with a coefficient of 1. Now, we started with that one because carbon only appears here in the third equation. So we know that that's what we have to do to that one. So we have to take that third delta H there and change the sign and multiply it by 1/2 to account for what we did. So that becomes minus 1220. Okay, so that's going to be what we do for that one. Now, here's the part where this one becomes a little bit trickier than the last one, because what we'll notice is that if we go to our second reactant, O2, O2 appears both in equations 2 and equation 3. So again, it becomes difficult if that shows up more than once in your given equations. How do we modify everything to get it right? We can kind of go forward with it now if you want to, because we've already modified this equation that has 3/2 O2. So we just to figure out how do we get one O2 on the product side. But we're gonna skip that for now, because again, if you have a reactant or product that shows up in more than one of the given equations, it's not usually easy to tell what you do with those to deal with that. So we're gonna skip that for now. We're gonna go to CO2 though, because CO2 only appears here in the first given equation. Now, what we notice is that CO2 is a product in the equation we're trying to find, but CO2 is a reactant in this first given equation. So we're gonna have to flip the first equation. So if we flip the first equation, we would get SrCO3. This is very similar to one of the other ones we worked through earlier, going to SrO plus CO2. That puts one CO2 on the product side, which is where it should be in the overall equation. So delta H for this, we just change the sign, which is going to be minus 234, change to 230 plus 234 kilojoules. So now we have to figure out what to do with the second equation, because these two equations here, they don't add up to the overall equation. The strontium carbonates cancel out, so that's good, but we have strontium and strontium oxide here that are in these two equations that don't cancel out right now, because strontium only appears on the left side of the arrow, strontium oxide only appears on the right side. So if we look at this equation here, number 2, what we can figure out, there's a couple of different ways of looking at it, but what we need is we need one SRO on the product side, one strontium oxide, one strontium on the reactant side. So this is flipped because we have strontium oxide on the reactant side. We need that's correct. So we need to keep this in the same order because we want strontium oxide to cancel out. So it's on the right side of the arrow here. So we want to keep it on the left side of the arrow so that it cancels out. But the coefficient for this is 1. The coefficient for this is 2. So we're going to just multiply equation 2 by 1/2. Now, the other thing that does for us is it's going to put 1/2 O2 on the product side, which will partially cancel out with a 3/2 O2 to give a net of 1 over there. So this one was a little bit more tricky to work for, but if we go through and make sure that our intermediates cancel, if we have this second equation here, we're going to get SRO going to SR plus 1/2 O2, and that will make sure then that strontium oxide cancels out. It's on both sides of the arrow, and strontium metal cancels out on both sides of the arrow. Delta H for this, we're just going to multiply the second delta H by 1/2 because we have the coefficients. So it's going to become 592 kilojoules. So there's different thought processes you can take, different orders you can approach that. So I don't want to suggest that the way that I did it is the only way to do it. But now we're ready to start adding everything up. So SR cancels out, strontium cancels out. We have carbon on the reactant side. O2 is one that, as I said, was a little bit tricky to deal with here because we want one O2 as a reactant. We have 3 halves on the left side. That's 1.5. 1/2 on the right side. So if you subtract those two, you're left with a net of 1 O2 on the reactant side. So this half O2 cancels out, and that changes the coefficient from 3 halves to 1. Strontium carbonate cancels out. Strontium oxide cancels out left and right of the arrow. So that's all that's on the left side. And then all that's left on the right side is what we want, which is CO2. So then delta H, we just have to add these three numbers together. Negative 1220 kilojoules from the first one that we wrote out, 234 kilojoules from the second, 592 from the third, and that comes out to minus 394 kilojoules. All right, so that's the most difficult one because we had, again, O2 appearing twice in the given equation, so it was a little bit hard to figure out what to do with that. All right, so any last questions on Hess's law? Now, what you might be starting to recognize is that this is kind of an impractical way to calculate delta H because we're just taking 2 or 3 random equations, adding them together. If we look through, tabulated data, there's going to be thousands and thousands of chemical equations that have delta H known. We have to figure out which ones of these should we pick out and how should we combine them. So it's not a very practical way to do it. So there is a more systematic and typical way we do this, which is by using what are called formation equations. So the first thing we have to do is define what a formation equation is, because essentially what we're going to be doing now is we're going to be saying, well, instead of just using a bunch of random chemical equations to help us figure out what delta H is, we're going to use exclusively formation equations. That's the way that it's more typically done. And a formation equation is a chemical equation that shows the formation of 1 mole of a compound from its elements. So what we're going to have is for any substance, we're going to have an equation that looks like that, and we're going to have delta H associated with it. And they're all going to be in the same format, which helps us then because it's not just a bunch of random equations anymore. We're going to be using these sort of standardized formation equations that are much more common to deal with. Now, one of the keys for this is that a formation equation deals with the formation of a compound from elements in their standard states. So we're going to have to define what that means a little bit. Another thing to keep in mind with formation equations is that fractional coefficients are okay on the reactant side. So when we first introduced chemical equations, we said, well, typically they're balanced with whole number coefficients. But for a formation equation, sometimes it's necessary to have fractional coefficients on the reactant side because your product side is going to have just 1 mole of compound, and the reactants are going to be balanced relative to that. So the general form then would always be elements on the left side forming 1 mole of compound on the right side. So again, the right side always has a coefficient of 1 exactly. And we balance the elements relative to that. So we do have to talk a little bit about standard states of elements to understand what those are and what they should then look like in a formation equation. So a standard state is basically the form that an element exists in here on planet Earth in normal conditions. So maybe if you go to some other extreme galaxy, that it might be a little bit different. But here on planet Earth with the typical temperature and pressure conditions, I think they're defined usually at 25 degrees Celsius and 1 atmosphere of pressure is the sort of standard state for these. So it's whatever the element exists at under those conditions. So you have to know, for that, you have to know both the state of matter, is it a solid, a liquid, or a gas, and the form, because some of them are going to be polyatomic, diatomic, or higher than that, okay? So there's going to be a few elements that are gases. This one I shouldn't have to tell you, but noble gases are gases. That's not, the name's not a lie. And then there's also going to be several other non-metal elements that exist as gases, and all of them exist as diatomic molecules. So hydrogen standard state is H2, nitrogen's standard state is N2, oxygen's standard state is O2, and then the 2 lighter halogen elements, F2 and Cl2. So those are all diatomic. Many of the main group elements are the P black elements, I should say, are like that. If you're on the right side of the periodic table, a lot of them are diatomic, and these 5 that I listed here are all gases. Now there's one thing that's nice. There's only 2 elements in the entire periodic table. Look at how many there are now, 118 or whatever. There's only 2 of those 118 that exist as liquids at standard states. So that's going to be, as you move down the halogen series, bromine, Br2, still diatomic, but it's a liquid and not a gas. And then a really cool one is mercury, Hg, which is the only metal that exists as a liquid. Okay. Fun to play with, but a little bit hazardous, so I wouldn't recommend it. Actually, elemental mercury is not that bad, but still treat it seriously. All right, so then finally, everything else on the periodic table, besides the noble gases and besides these 7 or so that I've listed, all exists as solids. So their state of matter is going to be solids for everything else. All of the metals except for mercury, all the rest of the non-metals that aren't listed here. But there are still a few other non-metal elements that exist as polyatomic molecules rather than just single atoms. So the heaviest halogen, I2, still follows the pattern of being diatomic. So you have F2, Cl2, Br2, I2. But as you move down, you go from gases at the top to liquid for Br2. I2 is a solid. And then some of the other ones that we've seen. So P4 we saw today, that's the standard state for phosphorus. It's a solid, but it's tetraatomic. And then the 2 right underneath oxygen, sulfur and selenium, exist as S8 and Se8. So they're solids, but they have 8 atoms bonded together into a molecule in their standard state, not just individual atoms. So it is important to be able to recognize standard states. For everything else that's not listed here as being either diatomic or higher order, the standard state is just the element by itself. So for all the transition metals, for example, all the metals really, the standard state is just the metal itself. Fe, Ag for silver, and then for manganese, whatever the metal is, that's the standard state. But for some of these, especially the non-metals, you do see higher order things that you want to be aware of. So then once we have a formation yeah. I mean, my suggestion is it's probably easier to download the PDFs, because if you have a million photos on your phone, it's going to be hard to keep track of. But however you want to do it, it's fine with me. Just here to give advice sometimes you don't have to take. All right, so then the standard enthalpy of formation, once we have a formation equation, it's going to have an enthalpy change associated with it, which we're going to define as standard enthalpy of formation. So this is defined as the enthalpy change associated with a formation equation. You will sometimes see it called the heat of formation. So that's not as precise of a term, I suppose, but remember, enthalpy and heat are closely related to each other. So if you see it called heat of formation, that means the same thing. The abbreviation for this is delta H, but then we put a little circle next to it, which indicates standard conditions. That, as we talked about, these are typically defined at 25 degrees Celsius and 1 atmosphere of pressure. And then a little F next to it to indicate that it's a formation enthalpy. So that's how I abbreviate it. Now, here's a thought problem here, because in most cases, if you need a delta H of formation value, we're going to give it to you. But there are approximately 118 delta H of formation values that you need to memorize. And those are going to be for, and I know you guys hate the word memorize, and so do I, but that's going to be for all the elements in their standard states. Now let's think about this for a second. If you have any element in its standard state, what is the enthalpy of formation for that element? Is it 0? Is it positive? Is it negative? Does it depend? And you do have to know all of them, so make sure you're familiar with this. Don't overthink it. All right, so let's think about this. If we have the formation of an element in its standard state, so if we're going to form hydrogen in a standard state from hydrogen in its standard state, what would be the delta H for that? Forming hydrogen gas from hydrogen gas. There's no change, right? Because it's the same reaction, same product. So there's no net reaction. That means there's no enthalpy change, because again, enthalpies of formation are defined as forming something from the elements in their standard state. So if the element is in its standard state, the enthalpy of formation is 0 because they're already in the standard state. So for every element on the periodic table in its standard state, delta H of formation is 0. We won't give that to you. You have to know it, but it's always 0. All right, so let's go through and then see how we can apply some of these concepts. So we're going to ask which of the following represents a formation equation. So we're going to talk about how to use formation equations to find delta H, but also you want to be able to identify them and know the concepts a little bit. So we want to know which of these represents a formation equation. So remember that the key aspects of a formation equation, we only want to have elements on the reactance side, and they have to be in their standard states. So you have to keep in mind what those are. And we should only have 1 mole of compound as a product. So if we go through these 4 choices here, this first one here doesn't have any elements in the equation. We have, and then on the reactant side, we have 2 different compounds. So I'll just underline those. So everything here is wrong. There's two compounds. We have 1 mole of compound on the product side, so that looks good, but it's forming from 2 different compounds, not from elements. So that one's not a formation equation. This one here, what we notice is that we have 1 mole of compound as a product, so that checks out. And if we look at the reactants, it's going to be all elements. Sodium, which is a metal, as a solid. Carbon, which is a solid. O2 gas is the standard state for oxygen. So that one looks like it would be a formation equation because it has 1 mole of compound, standard state elements. It is balanced. And again, you notice you need a fractional coefficient here because you have O2 is the standard state of oxygen, but you have 3 in the product, so you have to use a 3/2 to balance that. If we look at this one here, this one is not too bad, except that we see that you have a coefficient of 2 on the product side. Formation equations always represent the formation of 1 mole of compound, which means there should be no coefficient on the product side. So that one's close, but not quite. And then if we look at this last one here, 1 mole of compound on the product side, element, looks good so far, but we see that oxygen is present as just O, and O is not the standard state for oxygen. Standard state for oxygen is O2, like we saw up here. So that's going to be one that would not be classified as a formation equation either. So only choice B represents a formation equation. So C is just a formation equation, but the coefficients are doubled. And then D is not quite a formation equation because one of the reactants, this element here, is not in its standard state. Okay, so that's just identifying what a formation equation is. Yeah? What was wrong with A is that the reactants are compounds. The formation equation always has elements as reactants forming a compound, so there's no elements in this whole equation here. All right, anything else? All right, so then let's talk about how we use this to find delta H. So the nice thing is when we're using formation equations, even though it comes from Hess's law, even though it comes from the idea of taking a bunch of formation equations, flipping them, multiplying them, adding them together like we did before, we don't actually have to go through all of that effort to do it because if they're all in that standard form of being a formation equation, the equation for finding delta H becomes much simpler and we can just sort of generalize it and use it. So if we're using formation equations, we can say that the delta H for a reaction is just the sum. Sigma is a Greek letter that means sum of the delta H's of formation of the products minus the sum of the delta H's of formation of the reactants. So if we have the delta H of formation values given to us for the reactants and products, we just add up all the delta H's of formation on the product side, add up all the delta H's of formation on the reactant side, and subtract them from each other. So this Greek letter here is sigma, which you may have seen in the context of a math course, means that we're summing everything together. And then what I've indicated is M and N in here are the coefficients for each reactant and product. And we need that because delta H formation is defined as the formation of 1 mole of a compound, but if the coefficient for that is something other than 1, we have to multiply the delta H formation by that value to make sure we account for its contribution. And again, when we're doing this, if we have an element involved in the chemical equation, we can kind of just leave them out because their delta H formation is equal to 0. Okay, so you'll need non-zero values for all the compounds that are involved on the products and reactant side. Anything that's an element has a delta H formation of 0 could just be left out altogether and won't change the math. All right, so that's how we're going to do it. It comes from Hess's law, but it does not require us to add a million equations together and figure out how to modify them and combine them. So let's just do the combustion. I think we're towards the end, right? Yes, good. All right, so the combustion of methane, burning CH4, which is the major component of natural gas, in the presence of oxygen to make CO2 and water. We want to know the delta H for this reaction. Okay, and in this case here, if all we're given are the delta H of formation values, we have delta H of formation for CH4, CO2, and water. We don't have it for oxygen, but remember, oxygen O2 gas is an element in its standard state. So that one's not given to us, but it's equal to 0. Because it's an element, we have all the delta H's of formation for reactants and products. We can just use the equation I just gave. The delta H for the reaction is the sum of the delta H's of formation for all the products minus the sum on the reactant side. Those products minus reactants for this approach. All right, so what we have on the reactant side, we have 1 CH4, it's a coefficient of 1 there, the equation is already balanced. Delta H of formation for CO2 is minus 74.9. Sorry, we need CO2. We're starting on the product side. CO2 is our first product. Delta H formation is minus 393.5, coefficient of 1. Our second product is water H2O. Water has a coefficient of 2, so we're going to need to double that number. And the delta H formation for H2O gas is minus 241.8. So those are our two products. And then we're going to subtract from that the sum on the reactant side. So on the reactant side, we have 1 CH4. Its delta H of formation is minus 74.9. We have two O2s, but the delta H of formation for oxygen, because it's an element in its standard state, is 0. So that's what we have on the reactant side. So then just subtracting the two from each other, pay attention to all of your minus signs and make sure you're not missing any. What we end up with is minus 802.2 kilojoules. So we get a large negative number here. We subtract a small negative number, and we get minus 802.2 kilojoules. All right, this is a combustion equation, so we would expect it to have a negative delta H because we're burning something, and that's the number we get. All right, so any questions on that? So again, the nice thing is we could have written out all the formation equations. We could have tried to combine them like we did before, but because they're all formation equations, this shortcut will always be fine for us. All right, so just one other example, which is the preparation of phosphoric acid from red phosphorus. So it turns out that even though the standard state for phosphorus, as we just covered earlier today, is P4, which is called white phosphorus, and it is white in color. It also catches in fire if you put it in air, so it's a little bit hazardous. There's also this form of phosphorus called red phosphorus, which is just P by itself, not P4. So we have, in this case, because this is a non-standard state for that element, it does have a non-zero delta H formation for us, okay? So there's no elements in this case. The only element is phosphorus, but that's not the standard form, so it does have a delta H. But we have all the delta H's of formation given to us. We have 2 reactants, 3 products. All the delta H's of formation are given, so we can calculate delta H for the reaction in the same way. So on the product side, we have 1 H2O liquid. And the delta H of formation for liquid H2O is minus, I gave a lot of decimals here. I don't know why I was that precise, but minus 285.84 for H2O. We have 1 H3PO4 phosphoric acid. Delta H formation for that is minus 1271.7. So that's water. Didn't write this out before. Maybe this is helpful. Phosphoric acid, and then we have 5 NO2 gas. So we need to multiply that by 5 because there's a coefficient of 5, and NO2 has a delta H formation of positive 33.2. So usually it's signs that just get people on these types of problems. The math is not hard, but you have to make sure you don't forget any minus signs that are in there. So those are all of our products. I didn't write that very well. That's NO2. And then we're going to subtract from that the same thing on the reaction side. So we have phosphorus existing as red phosphorus, though, which is the non-standard state. So it's going to have a non-zero delta H formation of minus 17.6. Has a coefficient of 1, so we don't need to multiply that by anything except for 1. That's phosphorus. We have 5 nitric acids. And the delta H formation for nitric acid is minus 173.33. Those are the only 2 reactants we have, so we stop there. So then we just add all these together, subtract the 2. And what that ends up being is minus 507.29 kilojoules. All right. So adding and subtracting is about as simple as the math gets in a chemistry course. You just have to really pay close attention to the values, the coefficients, and the signs. All 3 of those things matter when you're doing this. All right, any last questions? All right, we'll probably finish chapter 7 next week and move on to chapter 8, which is gases.